This is the circuit symbol for an NPN transistor. There are 6 circuit variables for bipolar junction transistors that are collector, base, and emitter currents, collector to emitter voltage, base to collector voltage, and base to emitter voltage. Using KCL, we can write IE equals to IC plus IB, and using KVL, we can write this is the loop for KVL, VBC equals to VBE minus VCE. Please note that VCE means V collector minus V emitter. That means the node voltage at the collector or collector node voltage minus the node voltage at the emitter or emitter node voltage. BJT IB characteristics is the relationship among IB, IC, VBE, and VCE. The circuit symbol for PNP transistor is shown here. We have 6 circuit variables for PNP, just like we had it for NPN, and PNP transistors are similar to NPN transistors, with the only difference that when we label the currents and voltages for an NPN transistor, we're going to reverse the directions of the current. For example, for a PNP transistor, I emitter enters the emitter node, and I base leaves the base node, and I collector leaves the collector node. And voltage subscripts are going to be switched. So for the case of PNP transistor, instead of VBE, we're going to use VEB, just like here. And instead of using VCE, we're going to use VEC. The same goes to collector base node voltages. And again, VEC is equal to VE, the node voltage at the emitter, minus node voltage at the collector. The arrow in both PNP and NPN transistors are on the emitter terminal. So this is the arrow for a PNP transistor, and this is the arrow for an NPN transistor. These arrows are always on the emitter. For the case of NPN, the arrow points outside of the device, and for the case of PNP transistor, the arrow points inside the device. BJTs have 3 modes of operation. They're either cutoff or in saturation or in active region. The cutoff and saturation modes of operation are used when BJTs are used as switches. There are generally 2 types of applications for BJTs. They're either used as switches or as amplifiers. When they're used as a switch, they're going to be either in the cutoff region or in the saturation region. When they're used as an amplifier, they're going to operate in the active region. This is a circuit diagram for application of BJT as a switch. We're going to build the circuit in the lab and test it. In this circuit, our load is an LED, and we can use the BJT here to turn our load, which is the LED, on or off. And when BJT is in the cutoff mode, IC is equal to 0, so no current flows through the LED, and the LED turns off. And when BJT operates in the saturation region, a large current flows through the LED, and as a result, we can turn on the LED. So it operates as a switch. In the active mode of operation, however, we can use the BJT to amplify the voltage that is applied to the BJT transistor. Again, you're going to build the circuit in the lab and test the amplifier operation of BJTs. Let's see under what conditions the BJTs will operate in the cutoff or in the saturation or in the active region, and find out the IV equations of BJTs for each one of these modes of operation. Operation of a BJT requires the presence of emitter-generated electrons near the base collector junction. In other words, to have a non-zero collector current, the base emitter junction should be forward bias. So, a BJT is called to be cutoff if the base emitter junction is not forward bias. In other words, in the cutoff mode, I base is equal to 0, I collector is equal to 0, and using KCL, I emitter is equal to 0, and these current values are independent of the collector emitter voltage of the BJT. In the active mode of operation, base emitter junction is forward bias. In other words, BJT is not in the cutoff mode, and base collector junction is reverse bias. In other words, this VBC is a negative value. So base collector junction is reverse biased, and because I have this KVL, that means VCE is greater than or equal to VD naught. So a BJT operates in the active mode when collector emitter voltage is greater than or equal to VD naught and base emitter voltage is equal to VD naught. Here are the current and voltage equations that are valid for the active mode of operation. Please note that we are using an NPN transistor for deriving these equations, but these equations are similar for the case of a PNP transistor. For the case of a PNP transistor, we're going to change the subscript of the voltages and we're going to use the same equations. For example, when you have VB equals to VD naught in the case of an NPN transistor, for a PNP transistor, you're going to write VEB equals to VD naught. And here, instead of VCE greater than or equal to VD naught, for a PNP transistor, you're going to write VEC greater than or equal to VD naught. The third mode of operation for a BJT transistor is the saturation mode. In the saturation mode, the transistor is on. In other words, base emitter junction is forward biased and VBE equals to VD naught. We further divide the saturation mode into two regions, soft saturation and deep saturation, but for the purpose of solving circuit problems for this course, we are going to use deep saturation as the saturation mode of operation. But let's take a look at what happens in the soft saturation and how we can compare to the deep saturation. In soft saturation, base collector junction is forward bias. In other words, it's not reverse bias anymore. And VBC is greater than 0, but it is less than 0.4 volts. In other words, the diode that forms at the base to collector junction is forward bias, but it is not completely on. Because we have this KVL, we can write collector emitter voltage as a value between 0.3 volts and obviously it's less than 0.7 volts. So VC is greater than 0.3 volts, and in this region, we're going to say that BJT is in the soft saturation mode. In deep saturation, however, base collector junction is forward biased and the base collector diode is fully on. In other words, VBC is greater than 0.4 volt. These numbers are for the case of silicon. And again, using the KVL that we had, V collector emitter is a value between 0.1 volt and 0.3 volts. For the case of silicon, we're going to approximate VC with 0.2 volts and we're going to name it V saturation. So the current and voltage equations for a BJT operating in the saturation modes are I base is greater than or equal to 0 and VBE equals to VD naught, meaning that the base emitter junction is forward biased. IC, on the other hand, is less than beta times IB and VCE equals to V saturation. When the BJT operates in the saturation region, collector current is not equal to beta times I base, and if you increase the base current, the collector current cannot increase proportionally, and IC is going to be less than beta times IB. Beta is the current gain of a BJT. It is a property of a BJT device, and you can find this value or a range of values for beta from the data sheet for any BJT transistor. Transistor operates like a valve. We are using I base or VBE to set the value of current at the collector and collector emitter voltage. When I base is equal to 0 or base emitter junction is not forward biased, the valve is closed and IC is equal to 0. In the active mode of operation, I base is positive. In other words, base emitter junction is forward biased, so we have turned on the transistor, but valve is partially open and we can control the value of IC by changing the value of IB. In the saturation mode, IB is greater than 0, so the base emitter junction is forward biased, but in this region, valve is completely open, so I base does not control the IC value, or if we increase I base, IC does not increase proportionally. In other words, IC is less than beta times IB. In this mode of operation, IC and the VCE are set by the outside circuit that is connected to the collector and emitter. Here is a list of current and voltage equations for three modes of operation for an NPN transistor. Bear in mind that we are using a linear model for these IV equations. In reality, the current and voltage equations for a BJT are nonlinear and they have exponential format. And here are the equations for a PNP transistor using a linear model for BJTs. As you can see, these equations are similar to the ones that we use for an NPN transistor, with the difference that instead of VBE, for the case of PNP, we are using VEB, and for collector emitter voltage, instead of VCE, we are using VEC. In addition, the directions of the emitter current, base current, and collector current are reversed compared to the case of an NPN transistor. The collector current in the active region, in this region, is not constant for different values of VCE. In BJTs, when VCE increases, the width of the depletion region in the base collector junction also increases. As a result, IC is going to increase. This effect is called early effect, and if you extend the lines of IC versus VCE for different IB values, they're going to coincide at one point that is equal to negative VA. This voltage is called VA, is called early voltage, and it's a large value for BJTs. It's in the range of 50 volts to 100 volts, in that range. And the nonlinear equation for the collector current has a component that is related to VCE, and when VCE increases, the value of IC is also going to increase. Let's solve this problem as a practice and see how we can do this process. To solve this circuit, I'm going to first assume that the BJT is in cutoff mode. This means IB is equal to 0 and VBE is less than VD0. So I'm going to write KVL in this loop. I have KVL as 4 volts equals to 40K multiplied by I base plus VBE, and my KVL is complete. If I replace I base equal to 0 in here, then I'm going to have I base is equal to 0. I'm going to have VBE equals to 4 volts. This is greater than VD0, which is, for this case, we're going to use VD0 equals to 0.7 volts, assuming that this BJT is silicon based. So this is greater than 0.7 volts, so assumption was wrong and BJT is on. So moving on, I'm going to assume that BJT is in the active mode. Assuming BJT in active mode means IC is equal to beta times IB, and VCE is greater than or equal to VD0, and we are going to use beta value of 100 here. Now that we know that I base is greater than 0 and BJT is on, we can calculate I base using the KVL at the base emitter loop. So I can write I base equals to 4 volts minus 0.7 volts for base emitter voltage divided by 40K. That's going to give me 82.5 microamp. And because I know the relationship between IC and IB, I'm going to write IC equals to 100 multiplied by I base. That's going to be equal to 8.25 milliamps. Now I need to find the value of VCE to check it with the condition of the transistor operating in the active mode, which is this condition. VCE must be greater than or equal to VD0. So I'm going to use the second loop that I have for writing another KVL, and this is KVL2. Let me label it KVL2. Using KVL2, I have 12 volts or VCC equals to 1K multiplied by IC plus VCE. I know the value of IC, so I'm going to replace IC here equals to 1K multiplied by 825 milliamps plus VCE. From here, VCE is going to be equal to 3.75 volts, and this value is greater than VD0. As a result, our assumption was correct and this transistor operates in the active mode. In summary, we looked at the structure of NPN and PNP transistors. We looked at their IV equations for 3 modes of operation that are cutoff mode, saturation and active mode, and we solved a BJT circuit problem and calculated the current and voltages in this circuit. Thank you for watching.